So welcome to this deep dive into the future of green steel making. Today we will explore two promising reducing agent used to convert iron ore into metallic iron without carbon emission. One is hydrogen and another is ammonia. Now coming to our next slide, which is more about the stoichiometry of reduction, and where it shows that what is the requirement of both. To reduce 1 ton of hematite fully into metallic iron, roughly 213 kg of ammonia is needed. And here most important point is to that ammonia requirement is that we assume complete ammonia decomposition to hydrogen. Alternatively, hydrogen-based direct reduction require about 54 to 58 kg of pure hydrogen. This stark difference highlights the fundamental mass requirement when choosing between two reducing agents. And it is quite obvious because difference is too high. Now coming to the iron ore reduction. Now using hydrogen, hydrogen. Now when we use hydrogen reduces hematite through a well-established sequential mechanism like Fe₂O₃ react stepwise to Fe₃O₄ and then to Fe₄ and finally to metallic iron. So the only gaseous byproduct of this clean process is water vapor and making it highly environmentally attractive. So this reduction typically operate at temperature above 570 degrees centigrade, leveraging hydrogen's high diffusion rate to achieve efficient conversion. And it is quite obvious from the all diffusion mechanism while going through the reduction processes of the iron ore. Now, similarly, our coming to the iron ore reduction using ammonia. So, unlike hydrogen, ammonia doesn't directly reduce iron oxide at moderate temperature. It first thermally decomposes into hydrogen and nitrogen. This we have to remember. This we have to remember. First, ammonia gets decomposes into hydrogen and nitrogen, and for that we have to fuel that sort of energy to decompose it, and the hydrogen then participates in the same reduction pathway as direct hydrogen DRI. So emerging research suggests under certain high temperature conditions, ammonia itself may directly contribute to reduction and may partially incorporate nitrogen, leading to iron nitride formation. So our coming to our next slide, which is about a nitriding and the process control in ammonia reduction. So nitriding, the formation of a iron nitrides can occur in ammonia-based reduction, particularly dependent on temperature, and it is really dependent on temperature and nitrogen partial pressure. So these phenomena critically affect product properties and require careful processes control. So fundamentally, ammonia act as a hydrogen carrier with iron reduction chemistry governed by hydrogen released after decomposition. So now coming to our practical consumption and efficiency part. So a consideration, efficiency consideration, if you see this practical consumption and efficiency consideration, then hydrogen consumption in efficient DRI process closely approaches theoretical value around 38 kg hydrogen per ton of Fe₂O₃. In contrast, actually ammonia consumption ranges between 50 and 60 kg per ton due to incomplete cracking and side reaction, which already we have discussed in the earlier slides. So direct use of ammonia bypassing full cracking can reduce consumption by roughly 18% compared to cracked hydrogen, but ammonia still require a higher mass input due to molecular weight difference. So our coming to our next slide, which is about a key comparative insights. Hydrogen is inherently more energy efficient for direct local iron reduction applications. Ammonia, however, offer a significant economic advantage for large scale, long distance or export oriented supply chain due to lower logistic cost and potential to circumvent hydrogen infrastructure. Now coming to the parameter comparison, as we can see that temperature and energy hydrogen reduction operation, that is within a temperature range of 700 to 900 degrees centigrade, whereas ammonia reduction requires a slightly higher temperature, which is 700 to 1000 degrees centigrade, to account for both ammonia cracking and reduction. So we can say that in a case of ammonia, we need a higher temperature. So the reaction heat demand for hydrogen is roughly zero point 0.5 megawatt hour per ton for shaft heating, but ammonia demand more energy due to the additional cracking steps, and quite obvious also. Now, coming to the energy for hydrogen production and total energy uses, we can say that hydrogen production via electrolysis consumes approximately 2.75 megawatt hour per ton of iron, contributing to a total energy use near 4 megawatt hour per ton of crude steel, when including steel making energy burdens. Ammonia routes generally require higher overall energy due to additional cracking and energy demands, reinforcing hydrogen efficiency at the point of use.